Gravity is a force. It pulls things down. Every schoolchild knows this. You hold a ball, you let go, something grabs it and yanks it toward the floor. Isaac Newton wrote the law. Two masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. Done. Settled. 300 years of engineering, rocketry, and planetary orbits all confirm it. Gravity is a force, and it pulls things down. That is completely wrong, and I can prove it. Not wrong in the way that, oh, it's an approximation or it breaks down in some exotic corner of the universe. It's wrong in a deep, fundamental way. Gravity is not a force. It has never been a force. And once you see why, you will never look at the ground beneath your feet the same way again. But before I tear this apart, let me be fair to Newton. Let me show you why the force picture is so convincing. Because it is convincing. It's one of the greatest ideas any human being ever had. Picture the solar system. The sun sits at the center. The Earth moves in an ellipse around it. Why doesn't the Earth fly off in a straight line? Because Newton says there's a force reaching across empty space, an invisible rope tied between the sun and the Earth, pulling them toward each other. The Earth is constantly falling toward the sun, but it's also moving sideways fast enough that it keeps missing. That's an orbit, a perpetual fall that never lands. And the mathematics work beautifully. You can predict eclipses. You can aim a rocket at Jupiter and hit it. You can calculate the tides, the precession of a spinning top, the trajectory of a cannonball. Edmund Halley used it to predict that a comet would return in 1758, 16 years after his own death, and it did, right on schedule. That's power. That's a theory earning its keep. For over 2 centuries, Newton's gravity was the most successful theory in all of science. People called it the law of universal gravitation, and they meant it. Universal. Everything with mass pulls on everything else with mass. When astronomers noticed that Uranus wasn't quite following its predicted orbit, they didn't doubt the law. They said there must be another planet out there, one we haven't seen, tugging on Uranus with its gravitational force. They calculated where it had to be, pointed a telescope at that spot in the sky, and there was Neptune. They discovered a planet with a pencil and Newton's equation. Simple, elegant, done. So where's the crack? I'll tell you where. Newton himself saw it, and it bothered him terribly. He wrote about it in a letter. He said, and I'm paraphrasing, that the idea of one body acting on another through a vacuum with no mechanism, no contact, no medium, is so absurd that no thinking person should accept it for a moment. Those are nearly his words. He gave us the equation, but he never pretended to explain how the force gets from here to there. He just said, I do not feign hypotheses, meaning I describe what happens, I don't explain why. For 200 years, nobody could do better, so the question sat there unanswered, like a locked door in the middle of an otherwise beautiful house. Then along comes a man working in a patent office in Bern, and he notices something peculiar, something so simple that everyone had overlooked it. Imagine you're standing in an elevator, a perfectly sealed box, no windows. The cable snaps. You begin to fall. What do you feel? Nothing. You float. Your feet lift off the floor. A ball you were holding floats beside you. If you push it, it drifts in a straight line. Everything inside that falling elevator behaves exactly as if gravity had vanished, as if there were no force at all. Now turn it around. You're in that same sealed box, but now it's out in deep space, far from any planet or star. No gravity anywhere. But somebody has attached a rocket to the bottom, and it's accelerating upward. What do you feel? You feel weight. Your feet press against the floor. You drop a ball and it falls. Everything inside that accelerating box behaves exactly as if you were standing on the surface of the Earth. Einstein asked, can you tell the difference? Can any experiment, any measurement, anything at all, distinguish between being in a gravitational field and being in an accelerating box? The answer is no. You cannot. Not in a small enough region, not with any instrument. The two situations are identical. This isn't a limitation of our tools. It's not that we just haven't built a good enough detector yet. It is a deep fact about nature. Gravity and acceleration produce the same physics. Period. Now sit with that for a moment. Because most people hear it and think, well, that's a cute observation. A coincidence. A trick of the math. It is not a coincidence. In Newton's theory, this is actually a bizarre miracle that has no explanation. See, Newton has two completely different ideas about mass. There's gravitational mass, which determines how strongly something feels gravity's pull. And there's inertial mass, which determines how hard it is to accelerate something. There is no logical reason why those two numbers should be the same. They measure completely different things. One is about how you respond to a force, the other is about how you generate a force. But every experiment ever performed says they're identical, to extraordinary precision. Newton accepted this as a brute fact and moved on. Einstein looked at it and said, "This is not a coincidence. This is a clue, the biggest clue in physics." He later called it the happiest thought of his life. Why? Because if gravity and acceleration are truly indistinguishable, then gravity is not a separate force at all. It's the same thing as acceleration, and acceleration, we know, is just a change in motion. So the question becomes, why does an object near the Earth change its motion? Not because something is pulling it, but because the space and time around the Earth are not flat. Here's where it gets strange, and here's where most people's intuition revolts. So let me go slowly. I want to take this one step at a time, because if I rush it, you'll nod along and not actually feel it. And feeling it is the whole point. Think about what it means to move in a straight line. On a flat table, it's obvious. A marble rolls straight. But what about on the surface of the Earth? If you walk in a straight line on the globe, you trace a great circle. You end up curving, not because any force pushed you sideways, but because the surface itself is curved. The straightest possible path on a curved surface is not what you'd call straight if you were thinking in terms of a flat map. Einstein's great leap was to apply this same idea not just to space, but to space-time. The combination of space and time into a single, four-dimensional fabric. And here's the key. Mass and energy warp that fabric. The Earth doesn't reach out and grab the apple. The Earth warps the geometry of space-time around it, and the apple simply follows the straightest possible path through that warped geometry. The apple is not being pulled. It's coasting. It is doing absolutely nothing. It's the most natural thing in the world. A ball sitting on a table. Now that's the object being pushed. The table is shoving it upward, preventing it from following its natural path. You feel weight right now sitting in your chair, not because gravity is pulling you down, but because the chair is pushing you up. If the floor disappeared, you'd float, just like in that falling elevator. And that floating, that free fall, is the natural state of motion. This turns everything upside down, doesn't it? And we've been thinking about it exactly backwards. We thought the falling apple was the thing that needed explanation. Something must be pulling it. But in Einstein's picture, the falling apple needs no explanation. It's doing nothing. It's the stationary apple, the one sitting on the branch, that's being forced. The tree is pushing it, preventing it from following its natural curved path through space-time. Let me give you an analogy that isn't clocks or trains. Imagine two ants walking on an orange. They start at the equator, side by side, both walking in perfectly straight lines toward the North Pole. They're not turning. They're not swerving. But as they walk, they notice something. They're getting closer together. By the time they reach the top, they bump into each other. If you didn't know the orange was curved, you'd conclude some mysterious force must be pulling them together. An ant gravity. But there is no force. The surface is curved, and two straight paths on a curved surface converge. That's not a metaphor. That is, in a deep structural sense, what gravity actually is. Now, most people who hear about curved space-time imagine that space is bent in some dramatic way near the Earth, like a bowling ball on a rubber sheet. You've seen that picture. Forget it. It's misleading in about 5 different ways, not least because it uses gravity to explain gravity, since the bowling ball sags because of the very thing you're trying to explain. The real curvature that matters near the Earth is mostly curvature of time, not space. This is the part almost nobody appreciates. Time runs at different rates depending on where you are in a gravitational field. A clock on the ground floor of a building ticks slightly slower than a clock on the top floor. Not because anything is wrong with the clocks, not because of temperature or vibration or humidity. Time itself, the actual passage of moments, proceeds at a different rate depending on your distance from a massive object. This was measured, by the way. In 1959, Robert Pound and Glenn Rebka did it at Harvard using the Jefferson Tower. They sent gamma rays up a tower about 22 meters tall and measured the frequency shift. Gamma rays climbing up out of the gravitational field lost energy, their frequency dropped, and the amount matched Einstein's prediction to within 10%. Later experiments nailed it even more precisely. Time really does run slower near the floor than near the ceiling. In your own house, your feet age slightly less than your head. The difference is absurdly tiny, a fraction of a nanosecond over a lifetime. But it's real. And it accumulates. And it's not just a laboratory curiosity. The satellites that run the global positioning system, each one carries an atomic clock. Those clocks are up in orbit, farther from the Earth, where time runs faster. If you didn't correct for this difference, your GPS position would drift by about 10 kilometers every single day. The correction is not Newtonian, it's Einsteinian. Every time you figure out where you are using one of those systems, you're relying on the fact that gravity is curved spacetime, not a force. So if gravity is geometry, what happens when the geometry gets extreme? This is where it gets magnificent. If you take enough mass and compress it into a small enough region, the curvature of spacetime becomes so severe that nothing, not even light, can follow a path that leads away from it. The straightest path through that warped geometry always curves back inward. That's a black hole, not a thing that sucks stuff in with some tremendous gravitational force, a region where the geometry of spacetime itself is so curved that all paths lead inward, including the path of time. Time itself, inside a black hole, points toward the center, the same way that outside a black hole, time points toward the future. Falling into a black hole isn't like being pulled somewhere. It's like being unable to stop moving forward in time. The singularity isn't a place in space you're dragged to. It's a moment in time you cannot avoid. That should make the hair on the back of your neck stand up, because it means the everyday experience you're having right now, sitting there, feeling your own weight, is a symptom of curved time. Not curved space, not a force, curved time. And there's more. If space-time is a fabric that can curve, it can also ripple. Imagine two massive objects, say two black holes, spiraling toward each other. Each one has a mass 30 times the mass of our sun, crammed into a region smaller than a city. As they whip around faster and faster, closer and closer, they shake the geometry of space-time, sending out waves, ripples in the fabric itself. These gravitational waves travel at the speed of light, stretching and squeezing space as they pass. When such a wave passes through you, one direction gets a tiny bit longer, and the perpendicular direction gets a tiny bit shorter. Then they switch. You oscillate. Space itself oscillates. For decades, people built detectors to catch them. Incredibly sensitive instruments called interferometers, measuring changes in length smaller than 1/10,000th the width of a proton. Think about that. A machine so precise it can detect a change in distance 1,000 times smaller than the nucleus of an atom, and they caught them. In 2015, the detectors at LIGO picked up the signal from two black holes merging over 1 billion light-years away. The geometry of space-time shivered, and we felt it. Newton's gravity can't give you any of that. In Newton's picture, gravity acts instantaneously across any distance. There are no waves, no time delays, no ripples. The sun could vanish, and the Earth would somehow know instantly. Einstein's picture says no, the information travels at the speed of light, carried by the curvature itself. So let me come back to where we started. Gravity is a force that pulls things down. That's the story. And it's a perfectly fine story if you're building a bridge or launching a satellite into low orbit. The numbers work, the predictions are right, but the story is wrong. The mechanism it describes, a force reaching across space, does not exist. What exists is curved space-time. What exists is geometry. Objects move through time and space, and the shape of that time and space determines their path. No pushing, no pulling, just the natural tendency of things to follow the straightest available road through a landscape that mass has bent. You feel heavy not because something is dragging you toward the center of the Earth. You feel heavy because the surface of the Earth is accelerating into you, in a sense, preventing you from following your natural free-fall path through curved space-time. The ground is the thing that's interfering, not gravity. I find that astonishing. After 300 years of living with Newton's picture, after building the entire modern world on it, the truth is stranger and simpler and far more beautiful. There is no force. There is only shape. And everything, the orbit of Mercury, the bending of starlight, the slowing of clocks, the shudder of gravitational waves, the inescapable darkness of a black hole, all of it follows from one insight. Mass tells spacetime how to curve, and spacetime tells mass how to move. That's a sentence John Wheeler said, and it's about as perfect a summary as you're going to get. But don't let the neatness fool you. Behind that sentence sits one of the most difficult, most precisely confirmed, and most conceptually revolutionary theories human beings have ever produced. General relativity, a theory that says the stage on which physics happens, space and time themselves, is not fixed. It bends, it flexes, it responds to what's on it. The actors reshape the stage, and the stage redirects the actors. Nothing in our everyday experience prepares us for that. and we still don't fully understand it. We don't know how to reconcile curved space-time with quantum mechanics. At very small scales, the smooth fabric Einstein described should start to bubble and foam, but we have no tested theory for what that looks like. We don't know what happens at the center of a black hole where the curvature appears to become infinite. Is there really a singularity, a point of infinite density, or does something else happen, something we haven't imagined yet? We don't know whether space-time is fundamental, or whether it emerges from something deeper, the way temperature emerges from the motion of molecules. So the next time you drop something and watch it fall, don't think gravity pulled it. Think the straightest path through curved time runs toward the floor. The object was doing nothing. You were the one being pushed. And if that thought keeps you up tonight, well, good. That's physics working on you the way it should. I'd love to know, when you first heard that gravity might not be a force, what was the part that was hardest to let go of? Tell me. I want to know what your gut resists.